This is Fundamental Problem 18 from Chapter 14. The 4 kilogram collar C has a velocity of 2 meters per second when it is at A. If the guide rod is smooth, determine the speed of the collar when it is at B. The spring has an unstretched length of 0.2 meters. So we're going to use our work-energy relationship here. In this case, we have initial velocity, we have an initial height, and we do have springs. But if we look at a free body diagram for the collar C, we have a force of gravity, of course, acting downwards, and we have the force of the spring. We also have a normal force, which is perpendicular to the surface of contact, but the normal force is also perpendicular to the displacement, so the normal force does not do any work. And furthermore, because the guide rod is smooth, there is no friction. So the only forces that do work are the spring force and the force of gravity, but we're including the gravitational potential energy and the elastic potential energy, so work done by forces other than gravity is 0. Our initial point is A, our final point is B. We can put the datum at B and say this is where the height is equal to 0, and thus we can make the final gravitational potential energy 0. I know the mass, I know K, and I can figure out S for the spring at position A and also at position B. So I think I'm ready to plug things in. So I have 1/2 times the mass of 4 times an initial velocity of 2 squared plus a mass of 4 times g, which is 9.81. And then if this is the datum, then the height, I have to look carefully at the picture here. Okay, so the radius of this curve here is 0.4, so when we're at point A, the height is 0.4 plus 1/2 times k, which is 400 times s1 squared. Remember that s is equal to L minus L naught, where L is the current length of the spring and L naught is the unstretched length of the spring. So we're told L naught is 0.2 and the length of the spring at point A is 0.1. So the current length of the spring is 0.1 minus the unstretched length, this is 0.2, and it doesn't matter what the sign is for S when you're looking at the elastic potential energy because it's being squared. The work done by forces other than the spring force and the force of gravity is 0. So we can say this is equal to 1/2 times the mass of 4 times the velocity at B squared, which is what we are looking for, plus the gravitational potential energy at point B, which I set to be equal to 0, plus 1/2 times the spring constant K times S, which is the length of the spring when you are at point B. So that is going from here to here. This distance here is 0.4 meters. This distance here would be 0.3 meters. So the length of the spring when you are at point B, so I'm going to call this LB, is equal to the square root of 0.3 squared plus 0.4 squared, which is 0.5. So this is the length at point B, and S is that length minus the unstretched length, which is 0.2. And then we square that. Well, it should be pretty easy from this point to find the speed at B. 1/2 of 4 times 2 squared is 8. 4 times 9.81 times 0.4 is 15.696. 1/2 of 400 times, in parentheses here we have 0.1 minus 0.2, which is negative 0.1, and you square that, and so for that whole thing you get 2. Then 1/2 of 4 is 2, and this is 1/2 times 400 times 0.3 squared, which is 18. 8 plus 15.696 plus 2 is 25.696. And then we want to bring the 18 over to the other side, and then divide by 2, and then take the square root, and that gives us the speed at point B. And for that, I get the square root of 3.848, which is 1.96 meters per second. And let me just see what they asked us for. Determine the speed. Okay, so they're just asking us for the speed, not the velocity, and so the direction doesn't matter. And we get 1.96 meters per second for the speed at point B.